Tuesday we learned about Boolean algebra rules, laws. So we had an expression and we wanted to cut down that expression in its most simplest form, and the idea behind was to use the minimum number of wires and minimum number of gates so that we can save some space and while maintaining the efficiency of the circuit. Today we are going to learn about the canonic logic expressions, also referred to as SOP, sum of products, and POS, which is product of sum. Having the truth table is going to be the basis, and using that truth table we can actually derive an expression, and once we have that expression we can implement some kind of techniques including K-map or Boolean algebra rules and laws to further simplify it and then implement that simplified expression to create an application. But for today's lecture we are going to look at some of the truth table, and we are going to derive the expression, both SOP and POS, and do the implementation so we can verify the logic as well. Okay, here's a little theory about canonical form. In Boolean algebra, Boolean function can be expressed as sum of minterms or product of maxterms. Boolean function can be expressed algebraically from a given truth table by forming a minterm. Minterm for each combination of the variables that produces 1 in the output in the truth table, and then taking the OR of all those terms. Whereas the maxterms is the zeros in your truth table in a function, and then we take the end of all those terms. Sum of minterm, also known as sum of products, and product of maxterm, also known as product of sum. Boolean function expressed as sum of minterms or product of maxterms are said to be in canonical form. Okay, and then we usually take that canonical form and apply K-map or Carnot map or Boolean algebra rules and laws to further simplify it. Because we haven't covered Carnot map, so we're only going to apply Boolean algebra rules and laws. So let's start. Those of you who came late, there is some supporting material at the back. Please pick it up. Okay, all right. This is an example for exclusive NOR gate. Anybody knows what's the property of exclusive NOR gate? The output of exclusive NOR is 1 when the inputs are same. Okay, so if you look at the 0, 0, inputs are same, output is going to be 1. And if you look at the last one, 1, 1, inputs are same, output is 1. For the other combinations, the output is going to be 0. The symbol is pretty much, it's an opposite of exclusive OR, so it's basically exclusive OR with a bubble on it. So inputs same, output is 1. Okay, symbol we are going to have, so for a 2-bit we have 4 terms and usually we give them a symbol. So this will be like M0, M1, M2, and M3. Because I'm using different sources and different books, textbooks for this course, different books may have different representations. So I'm trying to expose you to as many, the way we use symbolic forms for different things. So M0 would mean it's a 0, 0, and M1 would mean 0, 1, and similarly M3 would be this 1, 1. This 3 in the subscript or is basically a decimal number. The sum of products, and because sum of products are the minterms, and minterms we know we're looking at the truth table are the outputs which are 1. So we have 2 outputs which are 1. One is this one right here, and one is this one right here. There are 2 things that you need to remember when actually driving equation for minterms and maxterms. When you are doing minterm, 0 is considered as A bar or B bar, whatever the variable is. If it's X, then it's going to be X bar. That is how you're going to represent it. Okay. If it's 1, you're going to represent as A or B or C. Or whatever the variable is. So let's say let's drive in Boolean expression for 0, 0. And also, yeah, so let me ask you, what is going to be the expression for 0, 0 in for the SOP? Remember, this is 0, so it's going to be A bar or B bar, right? How would you write a 0 in terms of the A in a minterm? Will be A bar, right? Correct? Because it's 0 and 0 is A bar or B bar. And what about B here? This is going to be B bar also, right? So it will actually make an AND gate. Notice some of the products is actually going to make an AND gate for each of the output which is high. How about this? What is going to be the expression for this 1, 1? Yes? AB, correct. AB. Okay, all right. So these are the minterms right here. And the product of sums are going to be the Maxterms. Maxterms are the 0 as output in the truth table. So again, if you look at over here, we got 2 zeros here. And things are a little different in the Maxterms. If you look at the Maxterms, 0 is considered as A or B or whatever the variable name is. And 1 is considered as A bar or B bar or C bar. Okay, so if I ask you what is going to be the expression for 0, 1 in Maxterm, what would that be? Come on guys, what is 0 here? In Maxterm, 0 is going to be A or B, so I can just write it down as A. What about 1? B is 1 and 1 is either A bar or B bar, so it's going to be what? B bar. Okay, and instead of ending it, we actually add it. Okay, what is going to be the expression for this term right here? 1, 0. A bar plus B, correct. Okay, all right. So there are different ways of representing minterms and maxterms. I know this might be a little confusing, but we'll do it so many times that you will understand that and you'll get it. Okay, so different representations. So let's say F is my output, okay, and we use this summation sign for the minterms. And the variables which are A and B in the subscript, and you open the parenthesis. Because these are minterms, so we are looking at ones in the truth table. And what are the decimal numbers for which the output is 1? 0 and 3, right? Okay, so it will be 0, 3. Okay, you can also write it down as M0, M3. Okay. Oh, sure. Thanks. Okay, so this is the decimal representation. Okay, and then finally we are going to write it down as the expression. So one of the expression was A bar, B bar, and then ORing it AB. Okay, so this is the expression for the exclusive NOR gate. Basically ORing the expressions, the individual expressions. Okay, in case of the Maxterm, you replace the summation with this pi sign. Okay, variables are again A and B, and for what decimal values you have the output as 0 here? 1 and 2. Okay, 1 and 2. You can also write down as A comma B, M1 comma M2, and then finally you take these terms right here, which is A plus B bar, and then you AND them together, A bar plus B. Okay, so this is your POS expression for the exclusive NOR gate. Ending the individual expression here. Okay, so again, remember, this is your SOP, sum of products, as the name itself suggests, and this is the POS, product of sum. Okay, if I make a circuit for this, logic diagram, okay, so this is the expression. I need two inputs, A and B, okay, and then these go into an AND gate, and both are bubbled. Okay, and then I also have going into another AND gate. And the output of these two will go into a OR gate, right? So this is my output F right here. Correct? Okay, similarly we'll do the logic diagram for this expression. So here I'm going to have two OR gates and one AND gate. Okay. This is A plus B bar. Then I'm going to add another OR gate right here. Okay, so A bar plus B. A bar, so bubble here, and then B right here. And they go into AND gate. And the output is the F, because this makes the AND gate here, right? Dot operator. Then F is right here. Okay, and they both will generate the same output. It's just a matter of choosing whether you want to go with Minterms when in terms of the driving the expression, or you want to go with Maxterms. If you have more Maxterms, you probably want to go with the Minterm, because the Minterm will be less. And we'll do more examples, so that would help you to evaluate whether you want to go with the SOP or you want to go with POS. Is everybody following me here? Right? Okay. Let's move on to the next example. Let's make some functional circuits. Okay. And this is going to be a half adder. Half adder is basically 2 bits and adding them. So again, 2 bits A and B. We have 4 possible combinations, 0, 1, 2, 3. When you add A and B, 0, 0, sum is? Come on, guys. 0 carry is 0, 0, 1, sum is 1. Carry is 0. 1, 0, sum is 1, carry is 0. And 1, 1, sum is 1, carry is 1. Okay. We are actually going to do SOP here. So remember, 0 is going to be A bar or B bar, and 1 is going to be AB. Correct? Okay, what is going to be the expression for sum? We look at what? We look at ones. Yes, you. Yes, you. You, not, yeah.
Is it the sum of 1, 0 carry 1?
1, 1? Yeah, that is right. That is right. Yeah. Thank you. Thank you. Yeah, that is correct. Okay, all right. What is going to be the expression for sum? Come on, guys. How many minterms do we have here? We got 2 minterms, right? And those are 1 and 2, correct? What is the expression for this one? Yes. A bar B. Okay. And what do we do with the minterms? We add the individual terms, right? Okay, plus. And the another minterm is right here. What is the expression for this one? Yes. A B bar. Correct. And if you actually notice from the truth table from the exclusive OR gate from the previous, this actually makes an exclusive OR gate, okay, which we know as this, okay. So this is an exclusive OR gate. So you can make this expression either with this expression or with using one exclusive OR gate. It's up to you. What is going to be the expression for carry? Carry has how many minterms? Come on, guys. How many minterms do we have for a carry? Look at this right here. There's only one minterm, right? There's only one output, which is 1. And the expression for that is going to be? Come on. AB. All right. Awesome. Perfect. All right. Let's make a circuit here. Do you want me to go with this expression or with this exclusive OR? Exclusive OR? Okay. All right. Okay. So here. Okay. So say this is my switch A and this is my switch B. Go in here. And this is actually sum, so I will just connect this to an exclusive OR gate. And I need an AND gate for the carry. Those are connected to A and B. Okay, and this is an AND gate. Okay, so imagine this could be some chip right here, and you basically have designed a chip which can do the half adder. It can take 2 bits at the input. You're providing users with 2 inputs, those are switches, and at the output you are providing LEDs. So what users see is these switches and these 2 LEDs. What is inside, you as a program, as a designer, have designed this. Okay, you got an exclusive OR in there and an AND gate. So you can basically, we have designed a chip that can do add 2 bits. So just verify whether it's working. Looks like these switches are set to 1, 1. So let's take that 1 and 1. So we get 1 here and we get 1 here, and also the logic at the inputs of the AND gate will be 1, 1. So 1, 1 going through AND gate gets you 1, right? So that means this LED is gonna light up, correct? Creating a logic 1. What about exclusive OR? 1, 1 is going to give you 0, right? So this will be 0. So you get 0 here, correct? So if you look at the truth table, we have been able to evaluate the truth table where when A and B were 1, both of them were 1, sum was 0, and then carry was 1. Okay? Let's move on to the next problem. Is everybody following me? Is if there's any single person in the class who didn't understand anything, I don't want to move on. This is a very important lecture, and we will be doing some more complex things in the next few examples. Is everybody good? Okay, all right. Awesome. Okay. Next example. So far, the couple of examples that we did, we had the truth table, or we drove the truth table, and then using the truth table, we came up with the minterms and the expression for it. Well, we can also reverse the process. We have the expression, and using this expression, we have to come up with the truth table. Okay. So let me ask you this: this expression for f, is this a sum of product or is a product of sum? It's a sum of product, right? So it is a sum of product. Meanings 1, 2, 3, 4. These four terms are what? Say it again. Yeah, these four individual products are basically four minterms, correct? Okay, we're going to refer it as minterms. Okay, so a bar we know is what? Is that 0 or 1 in sum of products? It's 0, right? So this makes a 0, 0, correct? This makes 0, 1, 1. This makes a code of 1, 1, 0. And this makes a code of 1, 0, 1. Right? Okay, now let's complete the truth table. For 0, 0, 0, f is going to be what? F is going to be 1 because it's in the expression. 0, 0, 1 is not here, so this will be 0. 3 is 1. 1, 1, 0 is 6. It's 1. And 1, 0, 1, which is 5, is also 1. So 0, 1. Okay, so we got 1, 2, 3, 4 minterms. 1, 2, 3, 4, and rest of the other are all zeros. Okay, so in decimal, if I wish to write, this would be 0, 3, 5, and 6. Okay. Now that we have the expression, we would like to simplify it. Okay. So here I can take a bar common. A bar common here. And then this would be b bar, c bar, plus bc. I know some students are not comfortable with using complement. If you want to use a bar, you can also do that. And here between these two terms, I'm going to take a common. So a here, and then I get bc bar plus b bar c. Okay. What gate this expression represents? B bar, C bar plus BC. Correct. This is exclusive OR right here. And you can actually look at it over here. A bar B plus A bar B was exclusive OR gate, right? It's just a change of variables here. BC bar plus B bar C is exclusive OR. And this is, we just did the first example, this is exclusive NOR. Okay, so if you look at the exclusive NOR example that we just did, F equals A bar B bar plus AB, right? You get B bar C bar plus BC. It's just a change of variable names, but logic is same. So I can write down the above equation as A bar, okay, and B bar C bar plus, this is an exclusive NOR gate, so the inputs are B, exclusive ORing with C, and because exclusive NOR is an opposite of exclusive OR, so I have the bar here, complement here, plus A. And how do we write exclusive OR? With variables input B and C, B plus enclosed in a circle C. Okay, so this is the expression, simplified expression we have. We can go with another exclusive NOR gate if we want to. And what would be the expression for that?
It would be A X NOR, B X
and bar on the whole thing, bar on the whole thing, right? So if you treat this as, say, A, and you treat this as B, right? So if you notice, it actually makes A bar, B bar plus AB, right? Which is again another exclusive NOR. So you can actually transform this equation into A plus B plus C, and then bar on the whole thing. That makes exclusive NOR gate. But let's just not worry about this part. We'll take this equation right here. Okay. Right. So I have written the equation right here. It's the same equation that we drew from the previous page. And now we are going to draw the combination logic diagram, and we're going to implement it. Okay. So I'm going to work on this exclusive OR gate first. So say this is exclusive OR, and then I'm going to have this AND gate right here. Okay. So here, the output of this exclusive OR will go into the input of this AND gate. And this A is just here. Okay. So this is my A, this is my B, this is my C here. Exclusive OR gate. So here, and then this is your AND gate right here. Okay, I'm now gonna, this expression is ready. I'm gonna work on this expression, so this one right here first. Exclusive NOR. Then I have this bubble. Again, the inputs here are B and C. This is my B here. And this is going to be the C. Here. And then I need another AND gate, and I'll just right here. One of the inputs going into this AND gate is this right here. And then I also need a bar. So I'll just squeeze a wire from here. Okay, this is going to be an inverter, and that goes here. Okay, so this is my A bar. Okay, this is my AND gate here. This is my exclusive NOR. And then what I do with the outputs of these AND gates, they go into OR gate, right? So another OR gate right here. Okay. OR gate, and this is going to be my F, the output here. Okay. Here you have actually your combination logic diagram, and you basically have implement. Do you want to try one combination? Want to make sure we got all our logic diagram right? Okay. Maybe we can go with, again, because the position of the switches is set to 1. So say we got 1 here, and 1 here. Okay, so 1, 1 going through an exclusive NOR gate is 1. And then this is A, right? So A was 1. Going through an inverter, it becomes what? 0, right? 0 and this 1. 0, 1 going through an AND gate is going to be what? 0, right? 0, 0 going through an OR gate will give you 0. Okay, so let's look at the truth table. When all inputs were high, 1, 1, 1, the output was 0, right? Okay. The only thing is I label my variables. Well, I can just go in here and then make this A, B, and C. Okay. All right. Does everybody understand how did we get to this logic diagram? It's really a simple process, but it's very easy to make an error. And that's why very important that you do the implementation part, basically just going through this circuit and then verifying a couple of combinations and make sure you're getting the right output. So that is one way of checking up whether you have the right diagram or not. We're moving on to actually it's a continuation of the same example. It says, now what if you want to design the same logic diagram using NAND gates only? Since they are cheaper, smaller, and faster than AND and OR gates. So our task would be to actually replace all these gates with NAND gates. And that, if you look at the lecture number 5, we had one of the slides where we discussed NAND gate as a universal here. Okay, so if you actually look at the bottom block diagram, I have, so each individual gate in the top block diagram represents a sub block. Okay, so if you look at, we got exclusive OR, so you got exclusive OR right here. Okay, and then you got AND gate right there, and then you got another AND gate below, and you got OR gate. So all those individual gates were used using the NAND gate. So if you look at right here, let's look at the OR. This is how you make a OR gate using NAND gate. You basically take two NAND gates, connect the outputs of those two NAND gates into another NAND gate. And this is what I just basically copy and pasted over there to the OR gate block. Similarly, if you take the AND gate C, basically you have two NAND gates connected to each other and you make AND gate using NAND gates. Exclusive NOR is this right here. So we're going to have to just copy this whole block into that vacant block in our sheet. So let's go back to the okay, all right. So okay, there should be a small gate in there also. Yeah. So I'll use this gate right here. Okay. So adding bubble to each of these. Okay. The output of these two NAND gates goes into this one. Okay, now it's about time that we start wiring them up. Okay, I have this exclusive OR right here. If you look at the exclusive OR, again, this is going to be our A, this is going to be our B, this is going to be our C. What are the inputs that goes into the exclusive OR here? It's easier to find it over here, right? Those are B and C, correct? Right? So I will actually feed B and C into these right here. You can use different colors. I'm using this is my B, and this is my C right here. Okay, what are the inputs going into this exclusive NOR gate? Yes, guys. B and C, right? So this is going to be okay. All right. What about the inputs going into this AND block? What are those? Yes, guys. Yes. A and exclusive OR. So this exclusive OR goes in here. And this is going to be A here. Okay, what about this AND gate? What are the inputs going in here? Yes, guys. Yes. Should that be A bar? A bar. Okay. Exclusive NOR is right here, so I'll just connect this straight away, and then I'll take A here. Okay, now because it needs to be an inverter, and how can I make an inverter using a NAND gate? Well, we can make an inverter using a NAND gate by actually taking this wire, feeding it to a NAND gate. So this is my NAND gate, this is my inverter, goes in here. Now the output of these AND gate goes to where? The output of these AND gates goes into the inputs of the OR gates. So we take this, and they go here, go here, and this is your F. Okay, all right. So basically what you have done, I've converted this logic diagram into another logic diagram which is only composed of NAND gates. We can simplify this further, but that is not the goal for today's lecture. What I can tell you, if you remember, one of the Boolean algebra rule and law was if you have a variable x and if you have a double inverter to it, it actually comes down as x, right? So in other words, if you have, say, 0 here, goes to an inverter, gets 1, it goes to inverter again. So you basically get 0. So if this was x, basically you get x here, correct? Similarly, if you look at this part of the circuit, what do you see in this part of the circuit? You basically see two inverters, right? And you can actually just delete this part of the circuit. You can just directly connect the output of this NAND gate to this NAND gate. You don't need these 4 NAND gates here because they are just acting as a inverter, right? And we don't need that. So this is pretty much it for this part, this example. Does everybody understand what we have done here? Cool. Shall we move to the next problem, guys? Okay. I just want you to fill this table, and actually I'm going to do it with you as well. So we all do it together. And when you leave, just leave that paper at the bench at the back. Okay. All right. So there's an example. Bill passes when 4 or more people vote for it. So 0, 1, 2, 3, 4, 5, 6, and 7. Right. So what are going to be the minterms here? What is going to be the output here? Bill passes when 4 or more people vote for it. So this is going to be 0 because this is 0. 1 person vote 0, 2 person vote 0, 3 person vote 0, 4 people vote 1, 5 people vote 1 because it says 4 or more. 6 people vote 1, 7 people vote 1, right? Correct? Let's get the minterms. So we are looking at 1s, right? And here we are looking at 0s for Maxterms. Okay, we'll start with the minterms. This represents A, this represents B bar, and this represents C bar, correct? Similarly, this is going to be A, B bar, and C. This represents A, this represents B, and this represents C bar, correct? And this one is basically all ABC. That was easy. Now for the Maxterms, this right here is A plus B plus C. This is A plus this is B plus this is going to be C bar, correct? Now this one A plus B bar and then plus C. And then this one is going to be A plus B bar plus C, correct? So let's come up with a simplified logical expression for SOP and POS both. For SOP, we take all the ones right here, right? So what do? We add them, right? A, B bar, C bar, plus A, B bar, C, plus A, B, C bar, plus ABC. Okay, this is your SOP. For the POS, here are the Maxterms, for which the output is 0, and we take a product of these individual sums. So A plus B plus C dot A plus B plus C bar, A plus B bar plus C, and then A plus B bar plus C. Okay. Which one? This one? Yes. Thank you. Yeah. Okay. All right. So you had your first quiz today. I'm going to finish here. There's one example that I could not do, but I would encourage you to do it at home. It's very simple. It's actually on POS. Okay. And I shall see you guys tomorrow. Okay. Thank you.